Hey everyone, and welcome to our second HuntersCON. I'm so excited to see hundreds of our customers, partners, and cyber practitioners from all over the world. Special thank you to our sponsor, Snowflake. Our partnership with Snowflake runs deep, and you will hear all about their vision for cybersecurity from Jake, Snowflake Cybersecurity Field CTO, in one of our sessions. But first, it's my honor to introduce Marcus Hutchins, one of the world's most famous cybersecurity researchers, to talk about the future of cybersecurity.
Thanks so much, Yuri. I'm super happy to be presenting at this con. We're going to be discussing Chrome's app-bound encryption and how it's sort of forced an evolution in the infostealer market that I would say has been much needed. It was not really designed to stop infostealers, but it has forced an important evolution. So to kind of get into things and set the scene, I'm actually going to walk us through how we might develop our own infostealer. So that's going to be kind of a fun little interactive exercise. So firstly, how does the Chrome Password Manager actually work? Now, one of the important things to understand here is that a lot of browsers are actually based on top of Chrome. So things like Edge and Brave browser, all under the hood are using Chrome. So if you are capable of building a Chrome info stealer, you also get a Brave and an Edge info stealer for free. Now, the passwords are stored in an SQLite database, which is just stored in the user's profile. I don't believe it's a privileged file. You can just grab the database file and read it. And it's as simple as just issuing an SQL query. So here we have an example of the output. As you can see, our fake user, John Smith, we get his username, we get the URL, but we don't get the passwords. Now, why don't we get the passwords? Well, Chrome encrypts some sensitive data. And I say some because I would personally consider usernames and URLs to also be sensitive data, but those are in plain text. So it is possible to just grab them without any effort whatsoever. But when it comes to passwords, they are encrypted with AES GCM. But the encryption key is also stored in the user's profile directory in a file that is named, I believe, something state. And here's an example of what the file looks like. We actually have two encryption keys. They're under the OS crypt object. We have encrypted underscore key and app bound encrypted key. Now, the app bound encrypted key is going to be important for later, but right now we're just looking at the encrypted key. Now, extracting that is super easy. It is basically 5 lines of Python code. We just need to grab the encrypted key field from the OS underscore crypt class. So we do still have one problem, and that is it is called encrypted underscore key, which does imply that the key itself is encrypted. And we could dig through the entire Chrome source code to find out how their encryption works. But if we actually search the encrypted key string in the Chrome source, the very first result that we get back tells us exactly how it's encrypted. It is with DPAPI, which is short for the Data Protection Application Programming Interface. Now, this is a very important thing to understand because it not just underpins the InfoStealer we're building right now, but also how their new InfoStealer protection works. So DPAPI, as I said, it stands for the Data Protection API, and it's basically Windows' built-in feature for encrypting data at rest. Each user gets their own private key, and that key is encrypted with the user's password, which means if the user is not logged onto the system and we were to say either we're another user on the system and we can grab their password, grab their key file, or we physically steal their machine and we exfiltrate all of the files off of it, we can't actually use that private key because it's encrypted with their credentials. So without knowing the user's credentials, we're pretty much dead in the water. Now, there is an interesting facet of how Data Protection API works, which is when the user logs onto the system, it automatically decrypts the key in the background with their logon credentials, and it stores it in secured memory unencrypted, which means while we're actually logged onto the system, we don't need to enter any passwords, we don't need to enter any keys. We can just call the function crypt protect data or crypt unprotect data to encrypt data and decrypt it retrospectively, and we don't need to enter anything. It's super transparent. You just bung the data into the function, call crypt protect data to encrypt it or crypt unprotect data to decrypt it. It's super, super simple. We've got an example of the same code in Python. It's super short, 15 lines of code, and we're able to unprotect the key. So this is just an example of how it works. We just shove the data in, get the decrypted data back, and here is our example code for actually doing the AES decryption. It's pretty simple. Again, only a couple of lines of code. We're just extracting the initialization vector out of the password block and then decrypting it with our unprotected AES key. So to put it all together, we have our extracting the key out of the config, unprotecting it by just calling crypt unprotect data. We don't need to supply any credentials or any keys as long as we run this code from the same account that encrypted the passwords, which if we're an infostealer, we are doing that. And then we just run the AES decryption and there we get all the passwords. Obviously, I don't think we needed to go this far given that the password is password123! We probably could have guessed that, but it's a good example. Now, the data protection API is not really designed for this. It's designed to protect data at rest against other users and against a device being stolen. But it's pretty flawed when it comes to protecting data on the current account. Because, as I said, we are using a single global key for all encryption done by that user. It doesn't matter if they're an administrator and a UAC, user account control elevated and up to full administrative privileges. Any data encrypted by that application is now decryptable by an application with low privileges, which is where infostealers really shine. They don't need to bypass UAC. They don't need to elevate to administrator. As long as they are running under the user that decrypted the data, that encrypted the data, they can simply decrypt it. So Chrome attempted to fix this. Now, for a bit of background, a lot of devices do actually provide application level segmentation. If you think something like iOS, apps get their own data store where they can store secured information, and other apps cannot read each other's data stores. So you get a nice, not just segmentation between users, but segmentation between applications. Unfortunately, Windows doesn't have this, and I believe Google actually asked if they would implement it, and they said no, which isn't really a surprise because this is the same company that took 30 years to disable macros by default, but it is a little bit of a problem. Now, Chrome basically tried to make app separation without the help of Microsoft. So they came up with their own technique to try and separate Chrome's passwords from the rest of the system without using kernel drivers or modifying the operating system, which is overall a losing cause, but it did actually have some good effects. Now, to understand how app-bound encryption works, I drew this very bad graph. We basically have now a Chrome broker process which runs with system privileges, so the highest privileges on a Windows system. And the Chrome broker process is now responsible for encrypting and decrypting the AES key. And if you remember in my earlier slide, I said each user has its own key. So previously we were encrypting the key with the current user's key, which meant anyone running under the current user account could simply just decrypt it. Whereas now we're actually encrypting it with the system key, which the user does not have access to. So the only way the Chrome process can decrypt its encryption key is by asking the broker process. So the broker process implements an API. The Chrome process goes, here's my key, can you decrypt it for me? And then the broker process replies back with the decrypted key. Now, if it isn't a Chrome process asking that question, the broker process can simply say no. So the isolation there is the Chrome broker process can decide whether it wants to decrypt the key or not based on whether the requesting process is Chrome or not Chrome. But how do we play hot dog or not hot dog? We have to actually look at the Chrome source to kind of get an idea. Now, if you're not familiar with modern C++, this probably looks like spaghetti code, so I'm just going to explain it. It grabs the handle of the calling process, which would in this case be chrome.exe, and then it does a basic path validation. So what's actually happening is it is just checking, is the path running from the Chrome installation directory? There is nothing else. It's not actually checking if the name is Chrome. It's not checking the digital signature. It's simply checking, is the executable running from the Chrome installation directory? It's a good start because there is actually a side effect of this. And because the Chrome installation directory is only writable by administrator, that means the stealer can't just simply copy its file into the installation directory and run from there, because in order to do so, it would need administrator privileges. But there are still plenty of bypasses. Now, the simplest bypass is code injection or process hollowing. Most Chrome processes run with the least privileges possible because they have to consider issues such as browser exploitation. And if someone exploits your browser, you don't want them to have system privileges. You don't want them to have even administrator privileges. So a lot of the Chrome browser processes are running with the least privileges possible, which means if we come onto the system as an info stealer with the least privileges possible, we can inject into that Chrome browser process, at which point we don't need to pretend to be Chrome. We are Chrome. So when we send that request to the broker process and go, hey, can you decrypt the key for me? It's going to give it back to us. And the same is true for process hollowing. We can run a Chrome process in a suspended state, run our code from inside that process, and it will pass that file path check. But this does have the downside of it's very, very noisy. Process injection, process hollowing, all of these techniques have been used for decades and decades in all of the world's malware, and EDRs are familiar with them, which means most EDRs do have rules, and very strong rules, to detect these techniques. So it's sort of forcing the info stealers to do stuff that is more overtly malicious. Now, another technique is, as I said, the key is now protected with the system key, which means if we're able to elevate to system, we can just decrypt it ourselves. We can just call crypt unprotect data from a system account, and we get the key back. But again, that's kind of tricky, kind of noisy. We have to either run a privilege escalation exploit to get to system, or we have to be an administrator, because there actually isn't a separation between administrator and system. Anyone with a UAC elevated process on an admin account can run system code. But again, in a normal organization, the user should not be administrator. So this is, again, very, very noisy and likely to trigger the EDR. And that brings us to the third and final solution, which is the one that most of the info stealers went with. Some did go with process injection, some went with process hollowing, some went with PrivEsk, but most went for this. And that is, Chrome has a remote debugging API. You can basically tell Chrome, hey, listen on this port and do whatever the port tells you to do. And I believe the communication is over WebSocket. So what an info stealer can do is launch a new Chrome process in debug mode and simply control it over the debug port. And one of the benefits of this is we don't actually need to go and parse that password database. We don't need to extract the encryption key. We don't need to do anything. We can simply just ask Chrome, hey, give us all the cookies or give us all the passwords, and it'll do it for us. The only downside is it's going to open a Chrome browser window, which if the user is active on the system, they're going to go, that's kind of weird. I think I might be infected with malware. So there's a couple of little tricks they like to use. One is to run Chrome in headless mode. It has a flag which is --headless, which basically means the Chrome process will run in the background rather than opening a window, which is a little bit safer. Another method is they can actually run the window outside of the screen coordinates. I don't know if this is a Windows quirk or something you can do on any operating system, but if my screen is here, I can actually run a window all the way over here. So one of the methods we've seen them doing is actually running the Chrome window at coordinates that do not exist within the screen's real estate. And finally, you have Create Desktop. If you're familiar with, I believe Linux and Mac have this, you can switch between desktops to avoid different applications cluttering up your main desktop. On Windows, there's actually a way to do this so that the user is not aware of the new desktop and they can just run stuff in the background. So a couple of the stealers have been seeing doing this. They'll just create a new desktop, run the Chrome process on that desktop, and then do the debugging to get the credentials. But Google actually knew this was going to happen. They were fighting with both hands tied behind their back. Without Microsoft's help to actually implement good application segmentation, they knew that they were just making a feature which would be bypassed. But they did something that was super useful here, and they raised the bar for info stealers while lowering it for defenders. Because now, as a defender, I can write EDR signatures for people running Chrome in debug mode or in headless mode or with coordinates outside of the screen. I can rely on the EDR's existing signatures for process injection and process hollowing, as well as privilege escalation exploits. So they forced info stealers to do overtly malicious activities, which is great because that was what the benefit of info stealers was. You have this older cybercrime info stealer, ecosystem, which was very botnet based. What you would do is you would infect thousands, hundreds of thousands, or maybe even millions of systems with a piece of malware, and you would maintain persistent access to that system in order to sell it to access brokers. But the downside of that is when you're running a big botnet with the same piece of malware running on millions of systems, now every EDR company is looking at you. Like every security company is looking for ways to detect your malware. So you're trying to exist on this system for weeks or months or years until an initial access broker can buy access. But the whole time you're fighting against every security company on the planet. It's a really, really hard game. And on top of that, you have all these botnet takedowns. The FBI does a lot of them. Europol does a lot of them. So you could spend weeks or years or months building a massive botnet, and then Europol just comes and deletes the entire thing, which is why we saw this pivot to info stealers in the first place, because info stealers don't work on maintaining access to the system. They just need to be undetected long enough to get onto the system, grab the passwords, and then get out. So that's why they've become more favored. Now, while botnets do still drop info stealers, it's getting more and more common to see hackers just dropping info stealers directly. They're not dealing with botnets anymore. We see them in malicious advertising. We see them in fake captures. So it's very popular just to directly drop info stealers because of how much easier it is for them to go undetected. But by doing this, what has happened is they've now forced info stealers to do a lot of the malicious behavior that was previously associated with botnets, which kind of brings them back into a lot of the downsides of the botnet. While they don't have to maintain persistent access, they now have to bypass a lot of very easy EDR rules to signature them, which does raise the bar for the info stealers and also lowers them for defenders. So that's all I've got for you. Thanks so much for listening to my presentation, and back to you, Yuri.
So yeah, Marcus, thank you so much for that. The presentation was fascinating. I think that one thing that I kept thinking about was just how elaborated the whole, ecosystem around infosealers and access brokers has to be in order to be able to, actually deploy, drop, extract, transmit the data, sell it, exploit it, and still have the credentials kind of like valid. And you gave a great example around passwords, but what we see a lot in the wild are actually cookies that have even shorter kind of like, expiration time. Is this really that efficient? I mean, is the ecosystem that fast in terms of like, the time it takes an info stealer to be dropped on a botnet until someone actually buys the credential on the other side and is able to exploit them?
So I'm actually not sure with cookies. I have my suspicion that when it comes to specifically session data, which as you mentioned is very short-lived, I think that takes a more direct path, and in a lot of cases, it's the person running the info stealer who is then using those sessions. But I do believe they do also try to sell them, but it's very hit and miss because you never really know what the session expiration date is. I know some of my sessions, they just stay logged in forever, and I've like never relogged into the account. But my average account, I'm logging back in maybe even daily or a minimum once a week. So it does have to be very fast. And when it does go to the market, someone has to buy that session data very, very quickly, or it's just going to expire. So yeah, I think you pretty much hit the nail on the head. It has to be as streamlined as possible. And in a lot of cases, they do actually have I call them side deals, whereas rather than taking the credentials to the market and just putting them for sale to the wider audience, they often work directly with the access brokers so that they can get the credentials to them as soon as possible.
Yeah. No, I mean that's fascinating, and I think that the other element of the whole putting the defender's hat on and thinking about how we as enterprises can protect ourselves against info stealers, or at least reduce the risk as much as possible. And you talked about EDRs and how much of an headache they could be for info stealers developers. But one of the things that we're seeing at Hunters is that a lot of those info stealers are actually getting deployed on non-enterprise endpoints that don't necessarily have enterprise level protection. And it's personal computer, someone is using it to log into an enterprise SSO provider, passwords are being logged and then shipped away. And I think that really opens up a really massive kind of attack surface around bring your own device kind of like policies. And that's something that, again, like a lot of things in security, is the tension between productivity and security. And I'm wondering how you think about it, and what you think that's kind of the next move from a defender standpoint.
Yes, I was actually discussing this exact issue quite recently because this protection, the entire foundation of it is to make info stealers detected by EDRs. But if the client isn't running an EDR, then well, that's completely useless. And as you pointed out, there is a big problem with bring your own device. A lot of people are working from their home systems. Their home systems are either not running an EDR or even an antivirus at all. And that is the biggest source of the credentials. So there needs to be more of a focus on, at least I think, if someone is not a contractor and they are an employee, they need to be running an EDR on their device. Ideally, I think companies should just be issuing company issued devices for all employees. But if they are bringing their own device, I think there needs to be an actual like a compliance criteria that says, okay, if you're not going to run our corporate EDR and feed all your data into our corporate SIEM or whatever, you have to run something that's good, like something that will actually detect info stealers. And I think there needs to be a lot more enforcement on not necessarily just taking control of the endpoint away from the user, because no one wants that, right? No one wants their company having MDM software on their home computer, but there needs to be some level of compliance, right?
No, that makes a lot of sense, and I think that another element of it is just putting more guardrails on sensitive kind of enterprise credentials, like SSO login, email login, other kind of pure enterprise software, and just have a very clear policy that these resources can only be accessed to your point, a company provisioned or company issued system. Um, yeah, I mean, I think one other kind of topic that I thought about as you kind of talked, which was really an interesting part of the beginning of your fascinating presentation. It was very clear that infostealers were kind of was a result of attackers thinking in the path of least resistance, right? There's it's becoming harder and harder to move laterally inside corporate networks. It's becoming harder and harder to stay, to your point from the end of the slide, on an endpoint and survive kind of EDR and endpoint protection. So why wouldn't we just build something ephemeral that actually steals identities and credentials, and then once you have the keys to the kingdom, you can get in whenever you want. And it's fascinating because, I mean, that's, again, attackers' ingenuity, right? Like the ability to kind of like, pick apart a very complex and secured system by targeting the weakest link in it. And I was wondering, when you think about, other novel approaches, or kind of like, similar trends in security, what other kind of like, interesting areas you're kind of like tracking? What are you seeing in the wild? What's the next gen in terms of like infostealers? Doesn't have to be infostealers, it could be also other things. But what should we think about in terms of like the next 5 to 10 years, or 3 to 5 years?
5 years, that's a hard one because I don't know what
Yeah,
tech
yeah, I
we're
know,
going to
no.
have in
5 years is
five
actually
years.
irrelevant.
Yeah. But
To
what
the
we're
next,
actually,
1 or 2 years, or 2 or 3
yeah,
years.
what we're actually seeing a massive shift in right now, which I've actually been putting out fires for the last month or solid on, is edge devices. People have realized that not only do edge devices such as routers, firewall appliances, VPN appliances not run any EDRs, they're actually incredibly poorly secured. They're full of vulnerabilities that are very easy for even unsophisticated attackers to exploit. So what we're actually seeing is a lot of attackers are realizing they can live on these edge devices. They can hide inside your router, they can hide inside your firewall, your VPN. And these devices typically are very privileged within a corporate network. If this is a VPN device, it's dealing a lot of the time with secure sign-on, it's routing connections within the network. So once they're onto that device, they have not just a good foothold within the network, but a better foothold than if they were on a workstation. Because not only do they not have to deal with an EDR, they actually have more privileges than an average endpoint would. So these past, I would say it's been going on for a little while now, but this past year, we've just seen attackers going absolutely crazy with edge devices.
Yeah, and I completely agree with you, and I think that you're spot on. And we saw a couple of like, really um, big kind of like vulnerabilities coming out against really big, at the end of the day, firewall and router vendors in the last couple of months. Do you think that like the main reason for that approach to be so kind of like, dominant is the how easy it became to kind of like exploit a vulnerability, or how easy it became to kind of like, weaponize a known vulnerability? Because firewalls and routers and VPNs were always kind of like the target, but it was always kind of like complicated and sophisticated. It was something that, the more higher end type of attackers went after. And I agree with you. I think that in the last couple of months, maybe a year plus, we see more and more kind of like commoditized attacks being targeting those edge devices.
I want to say it's a mix of two different things. The first is after COVID happened and we forced work from home, that kind of forced a lot of companies into this position of putting devices that weren't previously exposed to the internet onto the internet. So suddenly these VPN appliances that might have been, they might have had like IP allow lists, or they might have just been shut off from the internet entirely, started coming onto the internet to allow employees to connect from home. So you got this big explosion in all of these edge devices now being exposed to the wider internet. And that made a lot of security researchers interested. And security researchers started looking at these devices and they started finding vulnerabilities, and they ended up showing how easy it was. And then attackers saw that combination of not only is there now more devices exposed, but oh, it's way easier than we thought it was. And then they started getting involved too. And I think the most recent one I actually dealt with was a format strings vulnerability, which for those of you who aren't familiar with software exploitation is something you would have expected to see in the 90s or early 2000s, not the kind of very sophisticated chained exploit you would expect to see today. So a lot of it was there was this perception that it was actually a lot harder than it really was. But then when the attackers actually started looking into those devices, they were like, "Oh wow, this is full of holes."
Amazing, amazing. No, that makes a lot of sense, and it is something that is really important to bring into the attention of, not just our users and customers, but the industry. Do you see those edge devices being exploited by access brokers? Like it's something that already has an ecosystem around it? similarly to what you described with the infostealers?
So it's I'd say half and half. There was for a while a lot of access brokers were using uh, end-day exploits, so already patched vulnerabilities where public proof of concepts had been released, but we hadn't seen any access brokers actually finding their own zero-day vulnerabilities. But in the past year, we've actually seen not just nation-state APTs, but access brokers getting their hands on 0 days in these appliances and then just spraying the internet for them. So it went from very much security researchers are publishing these proof of concepts, and then the access brokers are taking them in and utilizing them, to now they're actually developing their own exploits.
And Marcus, before we wrap up, I mean, we can't really end the far side session around security without mentioning AI. What are your thoughts about AI? It doesn't have to be in the context of infostealers. What are your thoughts about AI in security? Could be from the attacker standpoint, defender standpoint. How do you see it?
So I've personally been quite anti-AI. I feel like people sort of jumped the gun with it. There was very early on when things like GPT-3 started coming out, people had this idea in their minds that if we give it enough data and enough parameters, it's going to become equivalent to a human. Like it's going to be able to think for itself. We're going to get AGI, and we're going to be able to solve all of our problems with these large language models. But what I think happened, and what I think a lot of researchers are starting to realize, is there's no amount of data that you can give these large language models, or no amount of parameters that they can support, where they're going to get, I'd say, significantly more sophisticated than they already are. So I think a lot of the technologies are now being built on this idea that, okay, AI right now is here, but in 5 years it's going to be over here. But what I actually think is going to happen is, I think we're actually either already have or are very soon going to hit the limit of the current models, and we're going to have to go back to the drawing board, come up with new models, and then we can progress and start solving all these problems with AI.
Yeah, and what do you think that the current models change from a security standpoint? Like, what impact do they have?
I think they allow us to condense data, right? I can put a 50-page report into a large language model and get it to extract the important points that are relevant to my goals, and 95% of the time it won't hallucinate something that just didn't exist in the report at all. But in a lot of cases, it is very good at summarizing large amounts of text. I don't know so much with things like IOCs. I've seen a lot of companies trying to get large language models to do sort of SOC work, which I'm a little bit skeptical about, but I have found it personally very good for firstly summarizing large amounts of data, and also prototyping very simplistic code that I can then go and build like a piece of software off of.
What do you think about at the end of the day, finding exploits and the ability also from the other side to be able to write more secure code by having kind of like, an AI co-pilot going through the code, making sure that at least, the example that you mentioned earlier, the exploit that you would expect from a 90s code, not to exist in modern kind of like, technology.
So I saw a very interesting research paper on that, and I think that is actually an area where AI is really going to shine, because a lot of the issue isn't that we don't know about these exploits, because obviously large language models, they work on the basis of, we have all this data and it can summarize all of the data, but it only knows what's in the data. So if we're asking an AI to find some completely unknown vulnerability that no one has ever seen before, it's not going to do that. But if we say, hey, just go and look at everything for all of these vulnerabilities you already know about, we're going to start seeing them falling out left and right, because the issue isn't so much that these vulnerabilities are so novel that no one can find them. It's that there's just so much attack surface and so much code to analyze that it's not possible to get enough humans to do it. So that's like one area I see these kind of large language models being useful for is they can just go and they can mass analyze code for trivial or known vulnerabilities.
Cool. No, that I also think that we're going to see a massive impact on that, and at least take the low hanging fruits from the hands of the attackers and the people that are looking to exploit those simplistic kind of errors. Yeah, thank you so much, Marcus. It was a fascinating keynote, and thank you so much for sharing the fireside with me.